Good, let's recap what we learned. So we started from this assumption. That's really the most important assumption for deriving the complex Ginzburg-Landau equation. We want a system close to a supercritical Hopf bifurcation where at wave vector equal to 0 you have an unstable mode that's associated with a finite frequency omega c at the transition. This implies this equation where the structure that you have in the linear term simply follows from the dispersion relation and the structure that you impose by translation and rotation invariance. And this term as well, G naught is the coupling constant, psi naught is the basic length scale, tau naught is the basic time scale, and these parameters, mu is the bifurcation parameter, as you see here. It tunes how close you are to the bifurcation point. C naught, C1, and C3 are the imaginary components. They're real, but they define the imaginary components in the bifurcation, in the Q squared term, and in the coupling. Now, when you are close to a transition, the band of wavelength goes to 0, and that means longer and longer wavelengths are the ones that dominate, right? So the physics is dominated by small time scales and long length scales. Long time and length scales, both long. And if I want my system to look the same on all these different scales, I need to rescale time and space such that mu drops out. And as you see from this equation, there's no more mu in the time or the length scale. And that means, independent of mu, the equation looks the same here. Of course, independent only insofar as you're close to mu equals 0. If you're further away, then the whole structure here can potentially break down. Good, now we want to analyze this equation in terms of its stability properties. And for that, there's different ways of going about. And one way, which is a very intriguing way and informative way, is by looking at the so-called polar form of the complex Ginzburg-Landau equation. And that means I rewrite back the equation in terms of its amplitude r and its phase phi. I insert that into the dimensionless complex Ginzburg-Landau equation, and I just sort the terms according to real parts and imaginary parts, and then you get two equations, one for the amplitude and one for the phase. And let me write them down, a bit lengthy, but that's what it is. So you get dtr is nabla squared r plus 1 minus gradient phi squared minus r squared r. So what this structure has up to now is terms that are gradients in r. There's a coupling between the phi and the r, and this term in the brackets, the 1 minus r squared, that makes sure that our amplitude r star is 1 in these dimensionless units. So it has a fixed point at 1 corresponding to the fixed point proportional to square root mu over g naught in the original variables. Then there's another term coming from the fact that we have the C1 here, and that has a structure r nabla squared phi plus 2 nabla r nabla phi, scalar product. So these two terms, they couple the dynamics in the amplitude with the dynamics in phi in different ways, such that gradients play a role here. And there's another coupling term, gradient phi squared times r. The equation for the phase, you can write like so. It's r times dt phi equals this term plus 2 times nabla r nabla phi. So all these terms are coupling terms that in a similar form appear also in the upper equation. There's another term where the C3 comes in now, C3 r to the third, and the C1 comes in here in nabla squared r minus r nabla of phi squared. Good, they look ugly, but that's what they are. Now let's say, just for you getting familiar with it, let's take a limit where we say that dtr is 0, meaning that the amplitude relaxes very fast to its steady state value, while the dynamics in the phase is slow. Okay, so we have a fast amplitude dynamics. And we also assume that gradients of r equal to 0. And that means that these gradients are really very, very slowly varying. So no gradients. When you do that, then you can just look at the equation for r. So this is 0. The gradient here is 0. This is non-zero. Here's also a non-zero term. So you can write from that r as a functional of the gradients in phi. And what you get by this is that r squared is slaved to the gradients in phi. Okay, so this may be a bit in quotation marks. Of course, there are gradients in r because r is slave to phi. What I mean is that in the equation for r, I'm neglecting the gradient terms in r. So you have this, and that's called adiabatic elimination. Such that our field R is no longer an independent field. It's linked to, in a local way, to the gradients in phi. So once you have that, you can insert that into the equation for phi, and then get a much simpler equation for phi, namely that this is C3 plus 1 minus C1 C3 nabla squared phi minus C1 plus C3 nabla phi squared. So when you look at that equation, that's nonlinear. Let's focus on the linear term, linear in phi. There's a constant C3 that shifts the dynamics. But here, that term is very important. What's its structure? As you look at it, it's a diffusion term. It's a diffusion coefficient times nabla squared phi. Such a dynamics is only stable if diffusion is positive. So this should be positive. If it's not, you will have an instability. So you can read off from this phase equation immediately that in the C1, C3 parameter space, there's a dividing line which is 1 equals C1, C3, such that at this dividing line, the diffusion coefficient becomes from being positive to being negative. So what we have here, there is negative diffusion or the same as an instability if 1 minus C1, C3 is negative. Right, and what this should teach you is, despite these ugly-looking equations coupling R and phi, the dynamics of phi plays a very important role because the phase relaxation to a steady state defines under what conditions the system goes unstable, and you have variations, strong variations in phi once you have a negative diffusion coefficient. Good, now let's go back to the full equation, not making this assumption, and now do the full analysis. So for that we look again at so-called phase winding solutions or plane waves. What we're asking is, are solutions of this type that are given by a constant amplitude times a plane wave with a wave vector and a frequency. So are those plane waves that I write down here, are they stable or unstable if I perturb a wave from a plane wave solution? Okay. So if you insert that into your dimensionless complex Ginzburg-Landau equation, so this one, you will get a solution for the amplitude. So from the CGLE, this solution must have an amplitude that's the square root of 1 minus q squared, and that's fine because the band of unstable modes is confined to the regime where this remains positive. And the frequency you get from that is minus C3 plus C1 plus C3 q squared. To make you familiar with what this is, so what is this for q equal to 0? For q equal to 0, this is phase factor in space is gone, so it's just e to the I omega qt. So it is a homogeneous oscillation. It's a spatially uniform solution with oscillation frequency omega naught equals to minus C3. if you translate that, maybe that's a side note that's not so unimportant. If you translate this to real variables, meaning original variables where nothing has been rescaled, this will be proportional to our bifurcation parameter times C3 over tau naught. Just to that you know that this is a rescale time by the factor mu. If Q is non-zero, then you do have here a plane wave, but a plane wave with a dispersion, and you may have seen this in electrodynamics, that you study plane waves with dispersion, and you know when you construct wave packets from plane waves with dispersion, these wave packets will have a group velocity, and the group velocity of plane waves with a dispersion, they are given by the derivative of the frequency that you have, omega q, with respect to q. And this is 2 times C1 plus C3 times q. And that's distinct, right, from what we had before. Now we have objects that actually move at a certain velocity. And before we had stationary solutions. Here we have the option of having solutions that move. And again, if you translate this back to our dimension 4 variables, then this has the scales coming from length and time scale. So it's length over time. That's a velocity. Then because q scales like square root of mu, there must be a square root of mu. And then we have C1 plus C3 times the original wave vector q. So meaning as you go to the bifurcation point, these things become slower and slower. The velocity, the group velocity, goes to 0. Good. Now that we have that, we want to know stability of that. So we ask, now what is the stability? So stability of that solution. And that means we need to make an ansatz that looks at perturbations from that solution. There's different ways you can do that. Last time we looked at deltas from that solution. Now I'm doing it a bit differently. Now I'm writing it as a general amplitude r of x and t, and a general phase e to the phi x and t. And I will look at the system such that I make an ansatz for the r. So the r of x and t should be the original rq plus rho of x and t. Okay. So I'm making a perturbation of the amplitude around the winding solution, amplitude rq. And I'm assuming that my phase that I have is given by the original phase, q times x minus omega q t plus phi of x and t. And my perturbations are these two terms. It's a density of deviations from a constant amplitude, and it's a density in the phase that deviates from the phase given by the plane wave solution. Okay. The rest is algebra. The rest means now I have to use that ansatz, have to insert it into these two equations, which are of the polar form. So I write for R here what I have on the right-hand side. I write for phi also what I have on the right-hand side. And then I'll just calculate from there what the equation for rho and phi is. And now just for me to make my handwriting simpler, I'm no longer writing this in terms of the variables capital Q and capital X and capital T. I go back just for notation to lowercase t and lowercase x and lowercase q, just for simplicity. Right. So I should write here t to be precise. Okay, so I get the following. For the rho dynamics, I get nabla squared rho. Then I do get the amplitude from the plane wave solution times the wave vector q dotted into a gradient of phi. And then C1 RQ nabla squared phi plus 2 times q scalar product with a gradient of rho minus 2 the amplitude of the plane wave times rho. This is, as you see, the linear part, just keeping here the linear terms on the right-hand side. It's linear in rho, linear in phi, and here as well, linear in rho and linear in phi. The equation for phi also has a term that goes like the Laplacian of phi. And then you have a similar sequence of terms that contain the amplitude of the plane wave and some scalar products of the wave vector with gradients. Now here gradient in rho. Then you have a term depending on C3 times RQ rho plus our coefficient C1, 1 over the amplitude, gradient squared rho minus 2 q times the gradient of phi. Right, so all not really complicated, just cumbersome to write down. You know how to go about this, right? Now you have an equation that's linear. There's gradients on the right-hand side. You further simplify that by making a Fourier ansatz. So we assume that rho and phi are Fourier modes with e to the minus k times x, where k is now a modulation vector that's on top of the q, right? The q was the plane wave that I assumed, and now I have additional modulations. Those are the k's. As you see, right, this is the original R, and that's modulated by a density modulation. The wave vector of that is given by k, and the same here. You have the phase, and now the modulation of phi that has this other wave vector k. Good, so for that, you then get a Jacobian, and this is minus k squared plus, minus 2 RQ squared minus 2I C1 QK. Then the off-diagonal element is 2I RQ, Q times K. Here we have I times 2 over RQ, scalar product between the two wave vectors Q and K, plus 2 C3 RQ minus C1 K squared over RQ, and then the diagonal element minus K squared minus 2I C1 Q times K. Okay, so that's what you get. That is the general result for the dispersion relation for a modulation of our plane wave solution. And now we want to analyze that and see, under what conditions you do have instabilities. One thing which is not quite obvious from the equation you look at, but maybe in hindsight, if you have looked at this more carefully, is that what really matters here are the long wavelength modes. They define when there is an instability. So let me write what we have here in the limit of long wavelength modes. So in that limit, the dispersion relation, which is a function of k, but also, of course, a function of q. So maybe I indicate this here as well. Sigma of k, but also of q, and of course also of all the parameters that you have. This dispersion relation has a rather simple form. It has a term that goes linear in k, and terms linear in k in a dispersion relation, they're indicative of traveling waves, of something that moves at a certain velocity. And this has the structure minus I times the group velocity as a function of k, where this group velocity as a function of k is given by 2 times C1 plus C3 Q times now k hat, and k hat is a unit vector, so it's k vector over amplitude of k. Now you see this is very similar to what we had earlier when we just looked at the group velocity in the plane wave solution. It has this structure C1 plus C3 times Q, and now it's a bit more involved. It contains the scalar product between Q and K. So then there's another term, which is a K squared term, and that then should be a diffusion term, and the diffusion term now has a dispersion, so it's not constant but depends on the wave vector. And what you get is that this is 1 minus C1 C3 minus 2 times 1 plus C3 squared over 1 minus Q squared Q dotted into the unit vector along K squared. Okay, so that's basically in the long run, what you do get, what's important from this linear stability analysis of the phase winding solution. Now, when you look at it, you obviously see that it makes a difference whether the wave vector k that characterizes the perturbation is along the original wave vector of the plane wave solution, or it's perpendicular to it. If it's along the direction of q, then this will give a finite value. But if it's perpendicular, it's gone, since the scalar product is 0. We distinguish now between those two cases, k being along the direction of q. We call this longitudinal. That basically means you are along the same direction where you have the plane wave, and the k is adding or subtracting from the wave vector, so you're compressing or dilating the wave that you have. So when it is proportional to it, then the parallel velocity is 2 times c1 plus c3 times q. That's exactly the original group velocity that I was talking about. And the diffusion coefficient is 1 minus c1 c3 minus 2 1 plus c3 squared over 1 minus q squared q squared. For the perpendicular direction, which is the transverse direction, so that means the opposite, you have a plane wave solution, and now you're asking at an undulation of this plane wave solution perpendicular to the wave vector q. And then, as said, the terms that are scalar products that are 0 now, and that means our diffusion coefficients and the group velocities are as simple as this. So now we're in a position to talk about the interpretation of it. Let's maybe look first at the transverse case. Okay, so what do you recognize in the transverse case? There's no group velocity, fine. The diffusion coefficient is 1 minus c1 c3. Look back now. This is this equation. It's the long wavelength limit because we neglected gradients here. And we arrived at an equation of the phase, which is basically what happens transverse to the longitudinal direction. And you see the same thing. The system becomes unstable if the diffusion coefficient is negative. Okay. So for 1 minus c1 c3 negative, you have a transverse instability. So the original solution that we assumed, the plane wave, is just unstable. Those transverse fluctuations, they will kill you and will make the original plane wave solution unstable. And something else will then emerge, and we'll see next time from computer simulations what this will be. Okay. For the longitudinal case, so let's go here. Now let's focus on the other regime, because we already know that if this is negative, there's nothing we can do anymore because things go unstable. So let's ask, what if this is positive? Then the transverse fluctuations are fine. Here, at first, the longitudinal fluctuations are also fine because that term is positive. It can become negative, though, if you look at the Q dependence. So for the other case, for 1 minus c1 c3 positive, what we do have is that you have an instability for a certain set of wave vectors namely for a wave vector q squared smaller than qe squared. And I call this QE because this is the same kind of instability that we encountered before for our stripes. It's an Eckhaus instability. And this QE squared you can read off from this equation. You just have to ask, when does that become 0? This becomes 0 if QE squared is given by 1 minus C1 C3 in the numerator and denominator, and in the denominator there's an additional term 1 plus C3 squared times 2. So with that, let me show you what this means. This means just this. You are now in this space where you plot on the vertical axis our bifurcation parameter mu. Mu equals 0 is the bifurcation point. For mu positive, you do have a bifurcation. The blue line, remember, is the marginal line. Inside of that marginal line, you have the system becoming unstable to spatial. The homogeneous stable state is unstable to spatial perturbations. So in this region where you are between the blue lines, you could have a plane wave solution. We made the ansatz of a plane wave solution and found that in the case of C1, C3 less than 1, meaning 1 minus this being less than 0, this gray band is unstable and doesn't have a plane wave solution. But these solutions, they are fine, they are stable. And remember from last time, that's the same structure as we had for the Eckhaus instability, where we also had this gray band of unstable modes and the white region where plane wave solutions are actually stable. So in that region, there's hope, because we do have this white regime between the dashed lines where plane wave solutions of the complex Ginzburg-Landau equations are stable and should represent the patterns you get. In this case, if C1, C3 is greater than 1, there's no hope. All the solutions that we made the ansatz for are actually unstable. Okay, this is how far I would go today. This shows you how we derive a complex Ginzburg-Landau equation and how we show that certain solutions, namely plane wave solutions, go unstable. Next time, I'll look into this from a numerical perspective, because I didn't tell you yet what happens if you are in these unstable regimes. What else happens? It can't be a homogeneous steady state. So what are the patterns that you get? It will be very interesting because there's beautiful patterns that emerge, including chaotic patterns. But you'll see next week. Questions?
Is there a way to say that how the arithmetic approach becomes exact when we consider?
Yeah. It's the long wavelength limit where the adiabatic approximation becomes exact. And that's what you see here from this structure, right? This is the adiabatic limit that we consider. And this is recovered here in the exact solution when you look at the transverse modes. Right? It's only the transverse modes that you cover with this kind of approach. You have no access by this approximation to the longitudinal undulations because you kind of eliminated them to begin with. You're focusing on transverse perturbations. Okay? So the long wavelength limit makes this exact for the transverse case. Other questions? All right. Thank you.